In this video, we're going to go through the first half of Exploration P.3, Cars and Goats, from the Tintle textbook. It reads, a popular television show, Let's Make a Deal, from the 60s and 70s, featured a car hidden behind one of three doors, selected at random. Behind the other two doors were less appealing prizes, such as goats. So when a contestant played the game, he or she was asked to pick one of the three doors, and if the contestant picked the correct door, he or she won the car. So you saw in the previous problem how I simulated that with three playing cards. Number one asked to suppose you're a contestant on this show. Intuitively, what do you think the probability of winning the car would be? So if I was in a regular classroom with you guys, instead of doing this online, I would ask students to kind of think about that. And pretty much all the time, students understand that it makes sense that the probability would be 1/3, that there's one car out of three doors. So if you played, it seems like there's a chance of winning of 1/3, a probability of winning of 1/3. It then reads, assuming there's no set pattern to where the game show puts the car, this game is an example of a random process. So although the outcome for individual games is not known in advance, you do expect to see a very predictable pattern in the results if you were to play many, many times. And this is called a probability distribution. We're going to explore this idea of what we mean by random process during this exploration. To investigate what we mean by all this, we're going to ask you to play this game many, many times. So in a regular classroom, I would ask the students now to actually get the three playing cards out, play the game once, shuffle, 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 play the game a second time, shuffle, 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 play again and again and again, 15 times, and fill in the chart to show if you won a car or a goat. So I'm just going to fill this table in with an outcome that I observed when I did this in a classroom and observed a particular student actually playing this Cars and Goats game with three cards 15 times in a row. Okay, so I've filled it in with what I actually observed happen when a student played this Cars and Goats card game 15 times in a row. Each of the little G's represent they played the game and picked a goat, or they played the game and picked a car. And it then asked in problem number 3, in what proportion of the 15 games did you win the car? So I'll note this particular student seems to have picked the car 4 times out of 15 times. It asks us to write this as a fraction, a decimal, and a percentage. So if you divide 4 divided by 15, you'll get the number 0.2666666. I'm going to just write that as 0.267. So as a decimal, it's 0.267. And if you write that as a percentage, it's 26.7%. In other words, this particular student that I observed won the car a total of 4/15 of the game. This student won 26.7% of the 15 games played. Okay, so this 15 trials or repetitions mimic the behavior of the game show's random process, where you introduce randomness to the process by shuffling the cards between the games. And the game show hosts, day to day or week to week when this game show was actually on, would shuffle which door the car was actually behind week to week. So to get a sense of the long run behavior of this random process, we want to observe many, many more trials, because it's not realistic to ask you to perform this thousands of times. It's not realistic to ask you to play this card game thousands and thousands of times. We're going to use a computer generator to do this for us. If you were to play this game 1,000 times, what proportion of those games would you expect to win the car? So we said above, we expect to win the car like 1/3 of the time. So I would say 1/3 of the 1,000 games. So how many games does that mean? Well, if you find 1/3 of 1,000, you'll get about 333 games. And I'm going to use the word about. I want you to also think about, do you actually expect exactly 333 games? Or would it be meeting your expectations if they won 332 games, 334 games? It's just please recognize when you say, what do you expect? You don't expect a very specific number. When you think that in the long run they win a third of the games, what you're really saying is that you expect them to get about a third when they play, somewhere around a third. Okay, so now we're going to open up a simulator. The only time we use this particular simulator in this class for this exploration P.3. So you don't need to bookmark this website or anything. This is just a website we're going to use for this one exploration. So this is a website that does the Monty Hall. Monty Hall is the game show, and it simulates. Down here at the bottom, it tells you that you want to run how many simulations of this. And I'm going to focus in over here on what's called the keep choice strategy, because that's what we're doing. We're saying there's 3 doors, pick a door, and that's the door that you keep as your selected choice. So it asks in number 5 here to play 10 games on the computer. So that's like me playing the game and picking car or goat, and then playing again and picking car or goat, and then playing again and picking car or goat 10 times in a row. But the computer is going to be able to do that at the click of a button. So I come down here and I ask it to just play 10 games right in a row. I keep the door that I select and I hit start. It shuffles, and it tells me right here that when I played 10 games, 2 of those games I picked a car, and 8 of those games I lost and picked a goat. It asked me in number 5 to record the overall proportion of wins that I get. So for this particular first set of 10, I could just write down 2/10, or I'm going to write that as 0.2 or 20% wins. Going back to the website again, it then says that you can start again, and it's going to play another 10 games. So I hit start again. Now notice, it doesn't just give me 10 games and the result of playing 10 games. It actually just adds to the previous ones. Now it's played a total of 20 times, and out of those 20 times, I've won the car 7 of the games and lost 13 of the games. So the total wins is 35%. 0.35, 35%. And I could keep going with this. I play another 10 games, so now I'll have a total of 30 games played. When I play 30 games, now it's up to 13 wins, 17 losses, for a total of 43% wins. So I keep doing this. I repeat and I repeat and I repeat, playing 10 more and 10 more and 10 more, all the way up until I've played a total of 100 games with the simulator. Okay, I've done it all for us. I went up to 100 games, playing 10 games at a time, and you see that it's kind of going up, in the percentage of games won is wavering around, up and down, depending on if I was winning more cars or more goats in my group of 10 games. By the end, at 100 games, I had a total of 28% wins. Do these proportions seem to be approaching some common value? You might not even be able to tell that right now, but it does seem to me that they're somewhere around upper 20s or maybe lower 30s, which makes me suspect that it might be that they seem to be getting closer and closer to maybe 33%, which is 1/3 of the games, like we suspected at the beginning of this problem. So it's not exactly 33%, but it seems to be kind of near 33%. We're going to repeat this simulation one more time, but we're going to start over. And this time, we're going to let the computer play 100 games at once, 100 games, and then up to 200 games, and then up to 300 games, all the way up till the computer has done 1,000 games. And I'm trying to understand that if you just play this over and over and over, what percentage of the games does it seem to be approaching that you win? All right, so back here, I'm going to clear results, start back at nothing played, and I'm going to change this to play 100 games at a time and keep the door that we pick. So I hit start. It says when I play 100 games, this time in the first round of 100 games, I won 28% of the games. I repeat, I add another, so I hit start again. Now it's up to 200 games, and it says in the total of the 200 games, you've won 31% of the time. Okay, I now used the simulator to play 100 games, play another 100 games over and over until it was up to 1,000 total games. The percentage of times that I won the car was 31%, then 32%, and then a total of 32, and then a total of 31. By the time I got to 1,000 games, it was up to 32% of the time I won the car. So overall, I would say that I won the car 32% of the time. And notice 32% of the time is really quite close to what we suspected as the true proportion of times you would win the car, which we said was a third of the time, which is 33% of the time. It's not exactly equal. When we say that we think that the chance of winning is a third, that you'll win a third of the time, again, we're not saying that when you play 100 games, you'll win exactly a third, or if you play 1,000 games, you'll win exactly a third. We're saying that if you play over and over and over and over again, you should expect that it will get closer and closer and closer to being a third of the games won. And that seems to be true. When we only played 100 games, we won 28% of the time, and it was wavering around and getting closer and closer to 33% maybe, but it wasn't hitting 33% exactly, guaranteed. When we played more games and went up to 1,000, it does seem to getting closer to 33%. And I would suspect if I upped this to maybe 10,000 games, it would get even closer to 33%. Overall, then, what I am taking from this and what I want you guys to take from this, probability of an event is the long run proportion of times the event would occur if the random process were repeated over and over indefinitely. And I also want to note simulation. We conducted a simulation to help us arrive at an understanding of the probability. Simulation, it says, is artificially recreating a random process under a specific set of conditions. The larger number of repetitions tends to more closely approximate the true value of the long run probability. So we suspected the probability was a third. And when we did 100 repetitions, it seemed to get kind of close to a third. But when we did 1,000 repetitions, it got even closer to a third. And I again suspect if I went up to 10,000, it would get even closer to a third of the games won. Long run probability, the more and more you do it, the closer and closer it actually comes to the true probability.